Hi, hello everyone. I'm David. This is Claudio. We are both from Atigio, a software company in Seattle. And the problem we are going to talk about today is the problem of finding out about financial fraud, specifically insider fraud, which is a big problem, basically because once it's done, it's extremely hard to undo. And this is about people basically stealing money. Money laundering, bribery, political contributions, breaking Chinese walls, insider trading, those kinds of problems. It is a major problem, so a lot of the funding for terrorism and money laundering goes through those kinds of schemes. It's also a problem because right now blanket regulations, as they often do, prevent a lot of service from poor people who are trying to move money between countries. And for the banks themselves, it's definitely something that they want to solve. Because they are being, other than the bad press that they are getting, they've been fined very severely. So for example, in the UK, in the 5 years leading to 2015, basically a quarter of the bank's profits went back to pay fines. So it's definitely a problem that's of interest to the banks as well as for society at large. So in terms of what we need to deal with here and why it's a hard problem. So the first problem to deal with when we started looking at the data, about 1 in a million messages is what you would consider a true positive, right? And a true positive is, yes, maybe this is something that human analyst needs to look at. It's not, that's definitely a case. This means that basically every qual classifier, traditional classifier you try to run against this would just tell you, look, you cannot be the classifier that tells you that all messages are fine. And you need to take a very different approach of anomaly detection. Even if you solve that problem, the next problem that you have is that there is no training data. There are only several hundred or at most several thousand cases per year. It takes 6 months or more to investigate a case, so you cannot crowdsource training data, right? When it takes a team of forensic accountants, several months to even decide if a crime was committed, meaning that you're not going to have enough labels. Okay, so you cannot train a model and come say, okay, here's my accuracy, let's go to production. You have to do this in production. You have to start with some baseline, get feedback from people, and evolve the system as you go. And the other reason you need to do this is because of the third problem, that we're dealing with some very creative and innovative people here on the criminal side. And as a result, basically every week, there's a new scheme that comes up. We've seen it in financial fraud. We've seen it in healthcare fraud as well, which is another area we've done a lot of work in. And what happens is, whenever someone gets caught, so all of us go into a room and we do a training and explain to you, look, here's what this person did, and here's how we caught them, and make sure you never do this. And if you're a bad guy in the audience, you take notes and you think about it. And one of the difficulties here is that in general, the people you're trying to catch know the area in a much deeper than we do. Okay, they're here, they have the relationships, they know the system, they know exactly where the problems are. So what you need to do, you cannot assume that, yes, I solved the problem, I'll deploy whatever I deployed and it works. Really the metric is, in production, day to day, month to month, as things change, does the system basically learn fast enough to remain effective over time? So to conclude, we have a real needle in a haystack problem. We have no training data. Okay, and we have really what's called an adversarial learning problem. So adversarial learning is a kind of machine learning where as soon as they begin to learn, the other side changes basically the training data and the responses to try to get me off track. So there are two things we need to do. One of them, as we said, is the feedback loop and learning in production, and the other piece is hybrid analytics. And by hybrid analytics, we simply mean they need to combine basically different signals or different hints from different types of algorithmic and mathematical approaches. So when someone does think about starting to do something that they should not be doing, usually they go through a process, and really the goal of the algorithm is to try to track that process and see what signals we can find, and you need multiple signals from multiple angles to get anything beyond noise. So when someone feels bad, first of all, they would think and talk differently. They would be disgruntled. They would be angry. They would think that somebody owes them something, and they would start showing it. Okay, that's usually the first sign. They would change their personal network. So either they would start working with groups they have not worked with before, or they are not used to working with, or maybe it's the opposite. Maybe they center all their business on one person that they're colluding with. You definitely need to look at the timing of events, changes from routine. So either I'm doing things on the weekend when nobody is looking, or I'm actually doing things at the, at the end of the month where it's harder to hide transactions in a much larger end of month stream that's happening. Obviously, at some point, I'm going to actually break rules. In the financial space, it's much harder than even things like, like tax, where you think you have books and books of flow. Here also, you're talking about hundreds of thousands of pages of regulation. And then on top of that, there are the unwritten rules of how the regulators, how the auditors expect to look at things, so how the law is interpreted. And then obviously there is teamwork and scale, which requires you to look above one person, and often it's 2 or 3 people who are doing something together. So in order to deal with this well, we need basically to build hybrid models, hybrid ensemble models, where we look at natural language signals, we look at time series signals, we do a lot of graph analysis and link analysis and get some features from those cases. We do need to do some rule inferencing. I mean, we do need to look at the rules to know what's going on. And then what you're getting there are different types of features. You cannot just go and build a classifier out of them, because if you build a classifier out of a wide range of features which are fundamentally different, what's going to happen is some of them are going to just be quieted away, and some are just not going to show up, because usually certain type of features, and really it changes depending on the classifier, certain type of features will tend to just overrule the others, either because there are just too many of them, right, because they are much stronger in a certain mathematical way. So the right approach is to build smaller classifiers by set of features and then build ensembles. And then what we need to do is retrain those ensembles as we get feedback really from the team of human investigators, right? Because I said, when we start, we don't know what we need to train for. We have some hints. We begin, we start getting feedback, and we learn over time. So what we've done here is we've taken some of the system we've built, and we basically created a free, based on completely open source library set of notebooks, so that you can download them, you can try this. It gives you basically the architecture of how this system is supposed to work. It gives you example which we'll go over about some of the types of features that we have created and how you apply the feedback and build models out of them. And for this demo, we've strictly stuck with some of the open source libraries, so you have those Python notebooks to look at. Python?
Okay, hello everyone. So essentially what we've done here is we took a classic email data set, which is the Aaron email data set, and we generated a stream out of it. And that's mainly to simulate some form of information that were captured through various communication protocols, unstructured data. And then we're simulating an account transaction based on a fairly sophisticated, I would say, algorithm, which is just on date time and just a transaction positive or negative in an amount. So those streams they produce data into Kafka. And then we consume data from Kafka using Spark streaming. And while we consume the data for every email, essentially, we go and extract what we called email level features or NLP features. And then out of the from and to of that email, we're constructing a graph. So we're appending, if you want, to a graph as it goes, as the data comes in. And then on the transactions themselves, we're doing very basic transaction level features, and we append this data into Spark SQL in a bunch of tables that then later we aggregate on a user basis and do some more advanced machine learning with that. So as we speak, just before we started this, I started this whole process, so let's take a peek into it. It's a live application, so bear with us for a second. It implies random number generators and all that should work. It seems to do work. So what we're seeing here is this is the job that's running right now. And I have essentially the 4 main threads running in parallel as you can see them. We have on the left side the generators for the streams, the transaction on the up and the emails on the bottom. And then on the right we have the processing threads running. And we can actually look at the actual logs. You can see this is how the transaction looks like. So you have an IP address, a date time stamp, and an email address and that identifies the user essentially, and a transaction amount. And then if you look into emails, you have obviously emails. Now we've altered a little bit these emails to contain some keywords, because if you just look at Enron, there's not too much fraud in that email, although everybody will believe that, yes, it's there, it's not. So, yeah. Now, live, as we speak, we have this IPython notebook who, using widgets, it's doing this polling. I think it's every few seconds, every 5 seconds or so, yeah. It's doing, and you can see the number of transactions being processed so far, number of emails being processed, how many graph edges we've added, and this continues to progress as we speak. So hopefully by the end, we'll see more bars on these charts. Now, down the bottom here, this is the only user that has been considered so far as being, of interest. And just because we have only one, the correlation metrics for this guy is not looking as it should be. Hopefully by the end we'll get to more people, and then the correlation metrics between the features for that user will look slightly more interesting. Good, now we go back to the slides for a second, and then we'll go back into another piece of code a little bit later.
Okay, so what you've seen so far is the basic streaming processes that process transactions. Right, so we have two jobs that just generate for the simulation emails and transactions, and then two jobs which process the emails and transactions and generate transaction level or email level features. But when we are looking for people here, nothing is going to be happening at the transaction level. Right? There's never going to be an email that tells you in bullet points, right, what people are planning to do. No, we haven't found one yet, anyway. So what you need to do is really you're looking for people. Okay, and you're looking for multiple signals at the person level. Therefore, what we have here is another layer of computation that's happening, and it runs in parallel. It runs as a batch Spark job, and we run it on a schedule. As soon as we have enough additional feedback or there's enough additional data, we run a new retrain process. And here's what happens. We start with the left, with the features we have generated, and then we generate basically similar features, but at the user level. So if at the email level, look at the sentiment of an email, at the user level, I'm looking at the average sentiment of the user. I'm looking at things like the change in user sentiment over time for different types of sentiments. I'm looking at things like the time series of, for example, if I'm starting to communicate later in the morning, I'm starting to come in later, there's a signal for something. If I'm changing my routine in some way that is interesting from just a time series analysis, and we go over some of that code. For the graph, it's interesting to look at specific images I've sent and specific people I've worked with or accounts I've worked with, but it's even more interesting to look at changes over time in how I communicate and how I work with people in general. So what we do, we generate those features at the user level. We add whatever feedback we have from the human agents, because again, the way the system works, they supply a list of leads to human detectives. They look at it and kind of say, this relevant, interesting to look at, yes or no, and that's the feedback that I apply here. And then what we do, and we do this in production, we go and retrain the user level classifier and reapply it. What happens over time is as I get more data, is things change over time, and as I get different kind of feedback, so I get different types of user behavior, different types of feedback, basically my machine learning ensemble model and the different, obviously, submodels change over time as well. So here you have the notebook that shows basically this process. At the beginning of the notebook, you can look at just the tables for, in this case, emails, and then afterwards the graph and the transactions as they come out of the previous stage. So you can see for an email, for example, we've parsed the email, we have datetime from to, we have parsed the basic, the subject, the content, and we applied sentiments. So in this case, a subject sentiment, a sentiment in terms of positive, negative, or power or submissive. So two types of sentiment at the email level. So we have those basic rules or basic features that we extracted at that level. And then we begin to generate the features at the user level. So one type of features that you have a separate notebook for is the time series feature. And here really we've just built using stats model, so I'm saying the basic, but really I think that the first useful and working examples of the kind of features you would want to implement if you were to build such a system. So one thing that we do initially is build ARM models, so autoregressive models, and we look here at both full and partial autoregression. Autoregression basically tries to look at the regression between a time series and itself as it's moved across different time zones. And it's a very simple and fairly effective way to identify routine. So for example, if I work using a basic, a weekly cycle, you would expect to see an autocorrelation spike at day number 7, right? Because my time series of what I do every day versus the same time series moved by 7 days should look fairly similar. We do this over different types of features. So here we are looking just in the number of transactions over time. And you can see, for example, for this user, we have a small spike at t equals 3. For this other user, we have another negative spike at t equals 10. And those imply basically different types of routines or different types of work that those users do. In general, as a tip, those are interesting. Changes over time in those routines are even more interesting. Okay, but basically we found that as long as you put the right data into it, ARMA and ARIMA-like models definitely provide a useful signal. Another thing we do with time series is looking for outliers. And here what we've done in the notebooks that you get are just a very simple ordinary least squares. So we can look at a person's encounters. We can do a simple regression, look at 2 standard deviations above and under what the regression line is. And one simple thing that you can do is simply count the number of outliers. So there are 2 of them here. And you have the code that actually does this here below. Okay, so those are some examples of what we'd be looking for at the time series level.
Yeah, some of the more interesting things that people like to look into, and at least everybody's fascinated about visuals, specifically complicated visuals. So people usually think about, oh, there's got to be something in a graph. The more sophisticated a graph it is, the more interesting to look at it is. So let's take a look at just the top 1,000 edges of this generated graph. So what you see, it's not a graph itself, but rather distinct subgraphs that happen to be or happen to form here. Now let's zoom a little bit, and you can see that some of these people obviously are better connected than others. Some of them, in this particular subset, right? They're kind of lonely, at least in this email communications thread that we looked at, right? But nevertheless, there's lots of interesting features that people can compute on the relationship or social graph, if you want, of interactions between these people. And what we chose to do here is we chose to implement what we call the degree of centrality, which is, it tells you how connected every node is, essentially, within the graph. And also a very simple metric, that is the number of nodes within the subgraph that particular node is in. Right? So it tells you, out of these 2, very generally, if that particular person is somebody that spreads a lot of information or consumes a lot of information, what's their influence? There's lots and lots and lots of theories and ways to do this, PageRank being probably the most famous in terms of algorithms to look into this. Again, this is just an example of how to do it. It's not our production system by any means. We have lots of other features. This is a sort of a tutorial, sort of a demonstration that anybody can look into. But it showcases all the steps necessary to do these things. So I'll go back now, after we look into these individual features, I'll go back into the notebook that pulls together. This is the iteration that runs on a scheduled basis to actually train a classifier against the feedback that we receive from the case managers. So here we do a bunch of, we apply the methods that we defined in those notebooks that we looked at all the data that we have, and it does a scale. It's using Spark behind the scenes. We just have a declarative language on top of that to make things easier for people like me. And after we do that, if we look at the set of features essentially that we get for every user, we have obviously features that come from emails and features that come from transactions. So all you have to do if you're using Spark SQL for this is just do a join. If you look at this particular join, you can actually see that that's what I'm doing. I'm doing literally a join between the table of transaction features and emails features, right? If you have a bunch of others, you can just generate n tables, just join them together. You put them all together into a nice, beautiful data set and play with it for modeling. The first thing that you want to do as a data scientist, obviously, is look at the data, see what, very basic things like what the distribution of the values of these features look like. Some of them carry some information. I would say if you look at these ones, others, not that many, or not that much information. The distribution is not that useful. Another important thing is you might be looking into a correlation metrics just to see between these features, maybe specifically if you have huge amounts of features, you want to look into how they correlate to each other and how they correlate with the variable we try to predict essentially, which in our case is the feedback. So here we're looking at the correlation metrics of these features just by themselves, and down the bottom, or here we added the agent feedback as the last row in this correlation metrics. You can actually see that some of the obvious things do show up, like the number of big transactions, for example, is very, very high correlated with the amount. Who would expect that? So, again, the number of outliers, it's anti-correlated with amount. That's how I designed it when I generated the stream. Okay. So after you do this and you inspect your features and you do some fair amount of feature selection, specifically have lots of features, right? Then you start doing your evaluation of models. And so just for everybody that didn't do data science by now, the ugly and most interesting on the same sense part is up to this point. From now on, you're just literally trying algorithms and try to optimize them. So in that sense, what's happening here is you split the data set. We took like 80% of the data we had so far for training and 20% for testing. We're training two classifiers, in this case, a stochastic gradient descent classifier and a random forest classifier with the default parameters. As you've seen in the previous slides, we're using scikit-learn. We literally live on scikit-learn. And in this case, if you take the default parameters, you see the SGD doesn't do anything. It's as flipping a coin. And random forest classifier does pick up some signal. And from time to time, you don't do this on production on a, let's say, daily basis, but you do it on a weekly or monthly basis. You might want to look into optimize your models. So the standard way of doing that is doing grid search over a set of parameters. There's lots of fancier ways of doing this. But if you don't have a huge amount of parameters, and if you have a big cluster, and you happen to run Spark on it, you can even use just a simple grid search to do the job of finding the optimal set of parameters, which is what we do here. So for the random forest classifier, we have the minimum number of samples per leaf within this range, and whether the criterion to split is Gini or entropy. You do the math of the size of the matrix of parameter space. If you go over that, you find the best set of parameters. If you retrain the classifier with the best set of parameters, you obviously obtain a close to perfect result because this is a canned demo. Good. In reality, if you see something like that, there's a problem. You probably do something completely wrong. Okay. Before we get back to the slides, though, let's look at the results. Let's see where we are so far. Hopefully, we advanced a little bit. Not too much. But there, you can actually see that the number of iterations increased. We processed more data. There's some spike here in the graphs. I don't know why. But apparently, a few more emails just added a bunch of new people. Although, for now, we only have one candidate, so the correlation matrix is still looking like this. Good. I guess that concluded a little bit the demonstration part of this, and let's summarize it. Thank you.
Yeah, so in summary, this is the kind of problem where people came to us and kind of say, we have all of this data, and we don't really know how to find bad people because they keep changing what they do, so just use your AI to find them. Which is not trivial, but basically there are two basic tricks that you need to remember if you're trying to do this. One thing is really to take the hybrid approach. Okay, so if someone tells you this is just a machine learning problem, or this is a time series analysis problem, or really what you need to do is focus on graph analysis, those will not work by themselves, and you really need that combination. That's one thing. The other thing that's interesting here, and I think in the demo notebooks you can see it, and I think it's a fairly general architecture for adversarial learning problems. You do need to do that machine learning in production. When it works, it's beautiful because it does feel like the system is actually learning, and you can actually learn from it after a while, right? Because it's advanced beyond what you've started it with. And you want to actually look at the coefficient, look at why it's actually bringing up certain people. Actually, I mean, the way we are seeing it, there are actually more and more problems where you need to do these kinds of things. Sometimes because it's adversarial, in other cases because you're dealing with dynamic systems and models do change over time. So it's very useful to have the architecture and system to begin with that can deal with that and make sure that at any given point in production you have a model that performs well. That's it. Thank you.
Cool. I want to thank David and Claudio for a great presentation. Do you have any questions? Please raise your hand. We've got about 3 minutes, so we can at least do that. Any questions, anybody? Sure.
So use multi-model.
Actually, use the mic here.
So the first thing is for the training data. I mean, each criminal has different feature, right? So how do you train the data? The second question is, you have multiple models, so how can you combine different models together?
Mm-hmm. Yeah, so in terms of training data, sometimes you have a handful of cases that you know about, or a handful of people you know about. Sometimes you don't, but you have other hints, right? So you can start with keywords or suspect behavior and look at people who are similar to those. But I would say in general, this is very different from classic training because there is no concept of training and test set, right? And no concept of cross-validation just because the number of true cases is so small. So really, the way you measure, right, is at the end, you go to the human detectives and you look at them and they tell you at the beginning, right? So are you giving me more true signals that are interesting to me to begin with? And then over time, are you keeping that rate, right, or improving it, right, instead of having some deterioration, which is what you'd expect from a static system. In terms of how we combine the models, so there are different methods of doing ensemble learning. One of the popular ones is doing a random forest where the different classifiers within the forest can be just different algorithms.
Or you can build a hybrid classifier based on, even if you put a simple one that combines any sophisticated models themselves. But the reason why you do that is not necessarily because the number of features is too high, but many times your features have different sparsity in their values, right? That's one of the reasons why you want to have different classifier trained on subsets of the data where the data is present for that particular feature. And then just use any kind of classifier to combine the results. So in layman's terms, just weight differently the individual models given the training label.
Cool. Okay, well, thanks very much. I think we're going to wrap it up right now. Appreciate it.
Thank you.